Okay, hello everyone. Thanks again for coming. Today it's my pleasure to introduce Marcelo again for the ones that haven't seen him here before. He did his PhD in Córdoba in Argentina, moved on for a postdoc in Canada, and now is a postdoc in Sissa in Italy, in Trieste. So without further ado, we're all yours.
Okay. So hello everybody. So first of all, let me thank Edgar for this very nice invitation to spend a few days here as a second time doing some research and having some fun with the calculations. Let me also thank Christian and as a new organizer of the CENTRA seminar. So thank you for organizing this and all of you for coming to the seminar. So today I'm going to be talking about what I have been doing during my first part of my postdoc in Sissa. This is a work in collaboration with other people, with Aaron Kovac, Mario Herrero Balea, Miguel Besares, and Enrico Barause. And what I will present here is the first step toward a more general and probably complicated program, which has to do with the numerical evolution of gravitational collapse in Orava-Lifshitz theory of gravity. So the outline of the talk will be the following. So first of all, I will spend a few minutes trying to motivate why wasting time thinking on modification of general relativity. I put some motivation because, of course, there are a lot of things that one could say about this, and I won't have a lot of time. And I am not a super expert on this because I started working just a year ago on this topic. So sorry if I will be happy to receive any questions. You can stop me whenever you want. Hopefully, I will be able to answer them. Then I will talk about two particular theories that I will be using, which I'm working here, which are Einstein-Ether and Orava-Lifshitz gravity. With them, I will introduce a notion of partial differential equation with what I call a Lifshitz scaling or anisotropic scaling that in this talk will be synonyms. Then I will try to motivate why those equations present, or which problems, numerical problems present these equations when trying to evolve them. After that, we'll present also an implicit scheme, which is a generalization of some previous work for any dispersive type field equation. This is like the heart of our project and the premise we aim to use in order to simulate the collapse in Orava-Lifshitz gravity. And finally, some application of this scheme for solving the Lifshitz field equation on top of a Lorentz-violating black hole test. At the end, I will say some conclusion and future works. So I think that there is no doubt that general relativity has changed since its proposal, the way of thinking and understanding space and time in modern physics. It's a theory that has been proved successfully on top of having very nice mathematical properties and being super elegant theory from a geometrical point of view. It has been tested experimentally, as you well know, not only in the weak regime, on the classical test on light bending or very helium-orbit corrections, but also in the strong regime. And I should mention here in particular two tests that I am really impressed and interested. I'm not experimentalist, but observational, but at least for reading, which are the binary pulsar, which first discovered by Hughes and Taylor in 1974. Even though the relative velocity, a binary pulsar is basically a millisecond pulsar with some other compact star. Even though the relative velocity between these two objects is small, of course the gravitational field in this surrounding is strong. And of course, I cannot not mention the direct observation of gravitational waves since 2015, which even though I would say good SNR is around 6, there are large uncertainties, but I would say that the theory has been tested in an outstanding way. So if we have this scenario, the question is why modifying? Why thinking on modification of general relativity? Of course, there are a lot of reasons. There are many reasons. I was just would like to point out two of them, one probably mostly observational and cosmological, and the other one most fundamental. The cosmological one has to do with precision tests, but basically the context is that we cannot explain with GR nor the origin of dark matter, nor the origin of dark energy. In particular, dark matter has to do with that using only GR is not possible to get accurate measurements of lensing dynamics of galaxy clusters. And in particular, the dark energy, which basically should explain the acceleration of our universe, cannot be neither from very first principles obtained from only assuming GR. From the fundamental problem, I just can say that we know that general relativity is incompatible with quantum field theory. There is no ultraviolet completion of CR. I'm not an expert on quantum field theory, and I don't want to do this. I'm more classical, but I have colleagues which are expert on that and basically help me to motivate my own research as well. So we have enough motivation. These two are just two of them, but believe me, there are a ton of other motivation on why thinking of GR just a limit of some more complicated and complete theory. These motivations and the others I didn't mention, but I am just telling that you should believe me, gave rise to what I call the zoo of modified theories of gravity. It's a very nice picture taken from a very nice paper, in which try to classify the ways in which one can modify gravity. We all understand which are the rules and the axioms of general relativity. So that means that if we want to go beyond or violate GR or modify GR or break their symmetries, there are some ways in which one. For example, considering higher dimensions theories, extra fields content, this is mostly with cosmologically motivated theories, as for example, scalar tensor theories or converting, which here in the audience there are a lot of experts on this. Or the other option is going beyond second order regarding the derivatives the order of derivatives that appear in the equations. In particular, the theory in which I'm interested in, which this work is inspired in Sorava gravity, which has an anisotropic scale, in the sense that we have second order time derivatives, but we have up to 6 derivatives in space. And this is mostly motivated from quantum field theory and from the fact that we are trying to look for a theory of gravity which is ultraviolet complete. So in order to motivate how can we go beyond second order, which implies in particular that we will be breaking one very beautiful symmetry that GR has, which is the Lorentz symmetry, is considering that I would say the most simple theory which breaks Lorentz symmetry, which is called Einstein ether gravity. So for Einstein ether gravity, basically is GR plus a unit time-like vector field, which is dynamical, is time-like, and has norm equal to 1 to -1, symmetry in this case is 1. Of course, this vector field, which is called the ether, is coupled at the level of the action. So there are equations of motion for this ether. And it trivially breaks Lorentz symmetry because now we have a preferred frame. Even though this action and this theory is diffeomorphism invariant, it is not Lorentz invariant. The dynamical fields are now the metric field and also the ether. And the action is basically the Hilbert action, and as I just said before, plus the most general contributions that you can consider, which are quadratic in gradients of u. If you, of course, there appear some constants which are dimensionless and which will play very important roles in the theory. Turning off or on these constants will give us different theories. So this is a family of theories, parameterized by these 4 constants. And of course, variating with respect to G or to U will give us the equation of motion, which are, for example, the one for G looks very similar to Einstein equation with some particular source. which is basically an energy momentum tensor coming with all the contributions, which are second order in derivative of u or first order as well. So it contributes in the principal part of the equation. And well, when you vary with respect to u, you get another equation which won't be important in this sense.
U dot is a time derivative.
Yes.
So you separate, and the nabla that was written there is on spatial.
Sorry, u dot is derivative along u. So it's ua nabla a. I'm not splitting yet. Because Einstein either you are not assuming u to be hypersurface orthogonal. That's what motivates my next slide. So the idea of Einstein either is very simple. You are breaking Lorentz invariance because you have this time-like vector field, and you have to think space-time with a particular frame which is time-like and is well defined at each point of the manifold of the solution. And it must be dynamical because otherwise you don't get the regular solution. So you really need equation of motion for you. So the question now is what happens if I, on top of that, require this u to be hypersurface orthogonal. So that means, of course, that I can foliate the spacetime with space-like hypersurfaces which are orthogonal to u. The labeling of these foliations are given by a function that I will call capital T. Since u is time-like, I can use this capital T as a preferred time coordinate. So I can choose coordinates adapted to the foliation, spatial coordinates adapted to the foliation, and use this frame as a preferred frame. If I decide to do this and plug all this information in my previous action, in the one I showed you before, SAE, which is covariant, I'm not choosing any coordinate there, any frame there. What I obtain is this action here, which is exactly the same as the one I had before, but the theory is different. Because now the ether, what I call the ether previously, doesn't appear here. Because these are all things that are related with the geometry, but the ether is hidden in the coordinates, in the coordinate choice that I made, particularly. So this is, as always, the intrinsic curvature of each one of the surfaces. This k is the trace of k, this 3r is the free-rich scalar, and this a is the acceleration of the time-like component. This theory, even though it is a particular version of the Einstein-Ether theory that I showed you before, has a particular name, which is called chronometric theory. Probably you hear about this. So chronometric theory and Einstein theory are practically the same. The difference is that for chronometric theory, you require u to be hypersurface orthogonal, and you need to write the action in that preferred form. If you don't do this, you are not in chronometric theory. So the difficult thing to understand now is that we are considering and we are using explicitly the Lorentz invariance for choosing a preferred frame. And the theory is constructed in that frame, not in any other frame. What does that imply? Well, simply that the theory is not diffeomorphism invariant, no longer. And the group invariance now is a bit smaller, which is that I call this, people call FD, which are foliation preserving diffeomorphism, which is this given by this transformation. You can rescale T, you can reparameterize time as you want. The only condition is this function to be monotonous, to be the derivative with doesn't change sign. And for the coordinate, you can do whatever you want, even considering the capital, the preferred time coordinate as well, in the new choice of the adaptive coordinates. Just let me mention that I here introduce, because of the literature is like this, wrote things like this, but I don't find any other. Probably I imagine that there are some motivation, but there is some motivation, but there's a relation, of course, between this C constant I mentioned before and the blue ones. And just the notation here is that C13 is C1 plus C3, C14 is C1 plus C4. Yes. Yeah. You can couple matter, just adding a term which is.
I guess my question is
probably
If you
minimal.
break Lorentz symmetry minus sector and forward sector.
Yes, yes. Mhm.
It's well understood how to calculate and still be.
In some particular cases, yes. In some particular cases. Still is an open problem because the theories are, for example, this is the. I will go a bit further. Just a second. So let me now turn the page and go into whatever Lifshitz gravity. So what I showed you before, which is chronometric theory. This theory is foliation preserving diffeomorphism, no longer diffeomorphism invariant, but it has only second order derivatives in time and in space. So this is what is called the infrared limit of a more general or ultraviolet complete theory, which is the theory proposed by Orava in 2009, which basically the action is the following. So this L2 is the chronometric action I showed you before. And there are some other terms, which are L4 and L6, which contains all the possible terms made up with the geometry, with the metric, which are fourth order in space and sixth order only in space. So all the time dependence, all the time derivatives will appear only in L2. So we will still get second order time derivatives and up to sixth order in space, in space, in spatial code. So this is not just because, and the reason is the renormalizability of probabilistic gravity, which is still an open problem. But you need to consider terms up to sixth order in order to have the chance to get the theory to be renormalized. Due to the fact that we have this anisotropy between the quantity of derivatives in space and in time, this introduces unscaling in the coordinates, which is this, which is what I call the anisotropic scaling. And this index here is related with the sixth derivative. In general, this 2 times this seat should be the maximum number of derivatives. You have to believe me this, I won't enter in details on this. But the theory is contract in this way. And in particular, the theory is contract in the preferred frame. You cannot change the frame because you don't have the symmetry.
Sorry, Marcelo, like,
yes,
could you say just a few words? Like, why would you need sixth order to have a chance for it to be renormalizable? Just in few words.
I'm not an expert on we can discuss probably later. I have a few words, but if I start talking of this, I will probably enter in a loop. But it's only related with QFT arguments and trying to kill the divergences that appear in the loop expansions, and probably some of people from the audience know more about this. But it has to do with it. When you consider all the loops, the possible loops you have, there appears terms that cannot be cancelled with the derivative you had before. So you need to add higher derivatives, and the maximum ones you need in order to cancel out all these divergences. You are safe if you consider up to 6 derivatives. Sure. Otherwise, you cannot get an ultraviolet coverage, basically.
That's basically is related to the constants appearing in front of the terms of the fourth order and sixth order term.
Mm-hmm.
They're not independent.
They are not independent. Exactly. You mean this?
Yeah.
Yeah. This is an energy scale, which has to be
It's
somehow
only one energy scale.
Mm-hmm. It's only one energy.
But you get to choose what M is.
I think there are some bounds for the energy.
But the bounds are observational.
Yes, I think so. But I'm not sure.
So in the limit where the scale is very large, you recover GR.
You don't recover GR, but you recover chronometric theory. You will be already you broke Lorentz symmetry, so you no longer have, unless you go to a particular theory in which I mean you can tune this lambdas, the constant in order to get the action if you want to GR, but in this preferred frame.
So the parameter that m lambda.
Those, or if you want, you can also think directly. Remember that there is a relationship with this. I found this version probably easier to answer your question, because if you just put n equal to 0, so you put this coefficient equal to 0, you recover GR. But this is in the covariant picture. So then you could do the analogous for this, choosing this lambda, eta, and g. Okay.
So C1 versus C2.
Yes, C13 is C1 plus.
When we talk about the infrared limit, exactly what is max?
Is a limit in which m is large. M goes to infinity.
And why infrared? I don't always get infrared.
No, well, because it's the way you count the energy. I mean, you count as
Okay.
1 over the energy scale. I'm also at the beginning was a bit confused, because if you want infrared, you should say energy going to 0, and I'm putting this mass going to infinity. So if you put mass going to infinity, 1 over the power of mass goes to 0. So it's the way this is parameterized. Okay, so in order to try to see how can we extract mathematical properties of this equation, because I didn't show you the form of L4 and L6, and you don't want to know unless you will work on this, or you have some students that probably could suffer. The equations are really horrible, but they are promising, because probably this is a theory of gravity which has an ultraviolet completion. And I think that is the only one which has this promise, okay? So the idea is, as the same way one does in GR, to consider a prototype or a toy model of the equation of motion. In the case of GR, which is a prototype, the wave equation. If you know how to solve the wave equation in the computer, you can pick up the Einstein field equations, put the harmonic gauge, and you will see that the equations are box of the metric and lower order time. The same happens with this Orava-Lifshitz beautiful theory. The toy model here, instead of the wave equation, you can still think, if you get lost at some point, you can still think on the wave equation. It's the Lifshitz field equation, whose action is this. This action actually appeared in some other context in condensed matter at some point for understanding some complex system. It appeared, but in this case appears specifically as the high energy limit, if you want, or the high frequency limit, sorry, of Orava-Lifshitz gravity, which is called the Lifshitz scalar field. So you can say that the first part is the action of the wave equation, right? This lambda there is the Laplacian of the induced metric on the hypersurface. We already remember that we have in this preferred frame. If you vary the action, you get this equation, which is the Lifshitz equation. So it's the box plus terms, which contains 4 and 6 only spatial derivatives. That means that when you do the mode analysis, you will end up with a dispersion relation, which, unlike the wave equation, when you compute the group velocity, you can have modes which are arbitrarily large group velocity, propagation speed. This may be problematic even in the well-posedness issue, because if we have this dispersion relation, how can we argue or assure that the equations are well-posed? Not only this equation, but probably is simple to see that it's well-posed, but the Orava-Lifshitz equations, which are a monster, how can we deal with the well-posed? This is still a work in progress. It's being, I think, ended probably soon by Aaron Kovacs. He was the mathematical part of the project. So thank you, Aaron, for illuminating us with this. But not only the Lifshitz field, but also seems that the Orava-Lifshitz equations are also well-posed. The way, just for people who work on well-posed, the way to show that Orava equations are well-posed is totally different to the usual way to prove in Sobolev space the well-posedness, because of the anisotropic scaling. So for proving well-posedness, one uses an algebraic way, which is called hyperbolicity. All the usual methods, probably you did some hyperbolicity analysis at some point of the equations you were working on. All these methods are no longer useful for proving these anisotropic scaling equations. So you need to first construct the method, prove that they are true. And once you have the criterion, go and prove the hyperbolicity with this new criterion for the Orava equation. And this has been done by Aaron, and I think it's work that should be coming out soon on Aaron. Regarding the stability, of course, there is also a condition of the coefficients in order this equation to be stable. In particular, the condition is that omega squared should be less or equal to 0. Otherwise, you will get modes that grow arbitrarily large. And the question always is, are these conditions enough in order to guarantee numerical stability of the equations? In order to answer this question, one does what is called the von Neumann stability analysis, which I also learned in this project, but it's a very common and useful numerical tool for proving the stability of a numerical method, not the stability of the equation. So just a few words on this. I will choose the easiest equation, which is the one-dimensional advection equation. With this equation, is ut time derivative, ux x derivative with propagation speed v. One way we could use in order to evolve numerically this equation was proposed by Lax. It's a very usual method from Lax in which you discretize space and time with delta x additive space and time steps. We will be using this notation f and j during all the talk. So this is the definition, is the function which is defined, is a function in R2, evaluated in our discretized grid in time and space. And then I will introduce what I call the Lax averaging, which basically means if you take the original equation, you can replace the time derivative by the corresponding difference operator. You can do the same, the one you want, you choose your favorite one. You do the same for the space derivative. But now you replace the value of the grid function u and j by the average of the values of two next points in the spatial grid at the same time. This is what we call the Lax averaging. And when you do this, you will get what I call an explicit scheme, which looks like this. So the reason to considering this or to doing this Lax average is otherwise you get an unstable method for numerically evaluating this equation. So someone had this illumination and said, if we change the value of the field by the average, this will also converge to a solution, and it will be in a stable way. This method I call explicit because the information of the field at the time at n+1 is only a function, it's an explicit function of things that has been already computed in a time step before. So the question is, how can I see that this method is stable? So what in general this von Neumann stability analysis does is to prove a local stability analysis. So you consider that the coefficients of the equations are locally constant and consider these eigen states or eigen functions as to be solutions of our equation. I introduce here a complex number, which I call psi m, which is called an amplification factor. If you plug this eigenmode in the scheme I showed you before, and of course require this to be a solution of the numerical scheme, that will give you a condition for the amplification factor. And since the solution scales as some power of this psi n, in order the system to give you a stable solution, is the stability condition hold, which is basically that the absolute value of this amplification factor has to be less or equal than 1. If you put this condition in amplification factor I showed you before, you end up with a very known CFL condition that I imagine that if you do numerics, you already deal with it. So what I show you is the mathematical proof of the CFL condition, and basically guarantees that all the information we need in order to compute the value of the solution at the point of the grid is inside the corresponding past cone. If we don't have this condition, we need information that is not still arrived, so we will get an unstable scheme. And this is the very well-known CFL condition. What happens when we have an anisotropic scaling? We are approaching to the Lifshitz field. So let me again insist with a very simple equation, which is the heat equation or the diffusion equation, which we already have an anisotropic scaling between the quantities of derivative in time and the quantity of derivative in space. We do exactly the same, the lax average, we compute the amplification factor, and we will get an equivalent of the CFL condition, but telling me that our explicit scheme will be, this explicit scheme, well, you can solve here, will be stable if my time step is chosen to be less than the square of the size of the spaces, which is not comfortable. It's not suitable, because if you want a very accurate simulation with a very small delta x, you will get to choose a time step which goes as a square of it. So it's super small, and you will get your whole life for evolving. And this motivates an implicit scheme. So going beyond explicit scheme, the first case was done by Frank and Nicholson, in which they realized that they could use this idea of the lax averaging in the spatial derivatives, not in the time derivative. It's not necessary, but yes, it is in the spatial derivative. So basically, this is the centered derivative operator of order 2 at time step n, and is averaged with the time step, the next time. If you do this, this method will converge to a stable solution, to a solution you were looking for. And now, if you compute it, if you do the Voigt-Neumann analysis of this scheme, which is implicit now, because you cannot solve for, you can see that that is implicit, right? Because you cannot solve for uj n plus 1 as an explicit function of un. You need to invert the matrix. You need to compute the whole grid once, right? So in that sense, it's implicit. If you compute the amplification factor, you get that the absolute value is less than 1 for any choice of delta x and delta t, which is amazing, because I can put, if I'm not looking for micro phenomena which happen in a very, very small time step, I can put the time step I want, and I can put the spatial step I want, and the scheme still will be stable, which is fantastic. So this motivated our scheme that we tried basically to generalize the Crank-Nicholson idea, but for an arbitrary anisotropic partial differential equation with anisotropic scale. I don't want to enter in the details. You can also follow our paper that has been recently published, but the most general equation we are working here is, in this case, just for the sake of simplicity, is for one field, which I'm calling psi, and in one plus one, so one spatial derivative. So we have second order in time equal to the function that depends on the coordinates, on the phi, on the time derivative of phi, some quantity of spatial derivative of phi, and some quantities also we allow, because it's a generalization of an arbitrary large quantity of spatial derivatives of the time derivative. We need to add this because that will happen in particular with the Lifshitz equation we want to solve. And we will apply this method for the Lifshitz equation. So of course, this is a second order equation in time. We need to give as initial data the field and the derivative of the time derivative. Just for a moment, let me assume that f is a linear function in psi, and in their derivatives. The dispersive character is obvious because since j and k are, in particular j, is arbitrary, we will have more spatial derivatives than time derivative. So the equation is anisotropic scale with some anisotropic scale. As is very common in numerics, we consider a first order reduction, which is a trivial one. We introduce a new field, which is a time derivative of psi, and consider the coupled system. Again, we consider this lax averaging for the fields, and when we replace these averages, we obtain what I call this discretized full implicit scheme. And it's full implicit scheme because the only way to solve this scheme, this scheme at time step n+1 is by ones in all points of the grid. So we need to invert the matrix. We are using here that the system is linear. The coefficients of the, first of all, the coefficients are function of the fields, to be function of the fields or the coordinates as well. And also the structure of this matrix is not arbitrary, it has some symmetries, and the symmetries comes from the fact that these matrices are constructed from the finite difference operator, which has some symmetries by definition, by construction. So the way, what we obtain is a Van diagonal system, which can be solved with particular methods for solving this linear system, which requires us order n iteration when n is the length of the spatial ring. You know that if you need to invert this matrix, you need to use the Gauss-Seidel, for example, inversion, which in general, this for arbitrary matrices, which are invertible, non-zero determinant, require order n cube iteration, which is not convenient. In these cases, we have the luck that we are lucky in the sense that these Van diagonal systems, which basically are generalization. Probably you know that the three diagonal matrices. Well, this is the same, but for an arbitrary quantity of up diagonals and lower diagonals with respect to the main diagonal of the diagonal. Okay, so basically this is the system. This V is a source, is another matrix which is very similar to this, and we need to add this vector, this column vector there for ensuring the boundary condition. That will depend on the problem we want to solve. But this is the scheme. I am assuming again here that f is linear because the Lifshitz equation is linear, so the principal part will be linear, and we can directly apply this method to this. Of course, it can be generalized to nonlinear equations, in particular the ones of Orava, that's the one that we want to consider. So what we did here, now I will go to the last part of the talk, which is applying this method to the Lifshitz field on top of a Lorentz-violating black hole. The first test we did, of course, was Minkowski, which was okay, but not interesting. So then we say, okay, what else? What can we do? What we can do? So solve this Lifshitz equation on a Lorentz-violating black hole spectrum. So again, I should spend a lot of time here talking about black holes in Lorentz-violating theory. What is a black hole in a theory that has arbitrarily large propagation speed? What is a horizon? Do we have black holes? Is a Killing horizon a causal boundary of the solution? If we always can have modes that have large and large velocity. Okay, I won't give a lecture on this, but what I will say is that the conformal diagram will have persons which are here experts on conformal diagram. So of course, what I say probably will be wrong. So sorry for that. But basically, remember that in these theories we are in a particular frame, but we were discussing minutes before. In particular, this is the way that the kernel diagram looks like. Those surfaces are the ones which are orthogonal to the chronon, to the time length, to the preferred time that I call capital T. Well, here this is this phi. Sorry for that. This phi is the capital T I had before. And the situation is that any even horizon like this, of course, can be escaped. So you cannot reach the singularity because you have this arbitrary large speed, or there are some modes. So that implies that any black hole solution have multiple horizons, even. And the reason is because of this anisotropic scaling and this dispersive failure of the equation. But there is a surface whose topology changes, which is this one. And the reason is completely related with the fact that we are breaking Lorentz symmetry, and we are assuming the particles to move in the positive direction, let's say, to the chronon, right? So once this surface is reached, and you are assuming that you are moving in the positive direction of the chronon, you cannot escape, and you will no longer. There won't be a way in which you can avoid the singularity. This surface, which is compact from a topological point of view, is called the universal horizon, and this defines a causal boundary of our solution. This is all what I would say about this. But basically, well, there are a lot of black hole solutions of Lorentz-violating theory, in particular in the seminal work by Berlin, David Mattingly, and then revisited by Barauza and collaborators. Look, for example, this solution is very similar to Schwarzschild, but we have this R to the 4th term. The solutions are analytic, and were already found, proven, everything. One can see that this universal horizon is reached when this function is equal to 0, and the value with this particular solution is at the fixed R, which has to do with this mu parameter that is here, which is the mass of the blank. So this is the background solution, and I will solve the Lifshitz equation using my implicit method that I showed you before in this background solution. Yes?
What is that A function? What is that function? Where does it come from? A capital A.
Is a way to parameterizing the search of the universal horizon. It has no physical meaning, as for example this A, which you can see. But if you see, this A appear as singular values, if you want, of the object. But remember that this ether has to be time-like everywhere, right? So yes.
Points inside or beyond the dashed line.
Yeah.
Are they all trapped surfaces? Or only beyond the line?
I think there are all trapped surfaces. Yes. I think there are trapped surfaces, but you can always escape at some point. Then because of the arbitrary large speed of some modes. So there is always a way to avoid reaching the singularity, right? And you will have also multiple horizons, but I think they are all trapped surfaces. I'm not totally sure, but I probably have to think a bit more than I would say. Okay, so the way I will use for solve the Lifshitz field on this background solution, I will go to the preferred frame, in which we know that we have a preferred frame. I will use this preferred frame. Now the ether, of course, looks like this because we are using the frame which points towards you, along you. This is the form of the metric, and also we choose, this is in spherical symmetry, so it's the final problem will be 1 + 1, just T and R. And I will choose just for convenience a tortoise coordinate similar to the one in Schwarzschild that pushes the universal horizon to -infinity. There are several ways to do it. We chose this particular transformation of coordinates. And at the end, we have to solve this equation, which is the Lifshitz equation, which I just change the name here for numerical purposes. It's easy to have just these two constants, K2 and kappa 2 and kappa 3, for testing the solution. So what we did was to consider, to exploit the spherical symmetry. So we basically did a composition in spherical harmonics in this way. If you plug this in the equation I showed you before, you get an effective equation. You can see that we have second time derivative, but up to 6 spatial derivatives in our start, and some effective potential, which depends on on R. That will play an important role for the different modes. Now we will analyze the solution of this psi LM, which will give us information on what is going on with the field when it, for example, enters the Killing horizon. So when we put this equation in our implicit scheme, we get something like this. These red letters here are the lax averaging of the spatial derivatives that I showed you before. The scheme turns out to be stable and convergent. I will show you this in a while. We prove two initial data. One is just a static Gaussian pulse, which is a Gaussian with 0 time derivative. And another one is an approximately ingoing pulse, because unlike the wave equation, it's difficult to have a perfectly ingoing pulse because of the dispersive relation we have. For the boundary condition, this is the reason. It was not possible to decouple the modes in a way we can kill the mode we want to kill, ingoing or outgoing. So what we did is to put a dissipative layer, which is a function which is 1 in the whole physical region if we want to analyze the solution. So we won't be changing the solution in the physical region. We will analyze the solution, but very, very far from the physical region, we will require this function to smoothly decay to 0 in order to kill the mode and mimic the wave disappear in the numerical domain. Of course, we need to test. This is a bit nasty if you want, but we need to test that this method works. And I won't show you here, but we have in the paper a plot which shows that our solution doesn't change that much when moving the position of the lane. But this is this is the way we will treat the boundary condition. Of course, it's not the best one, it's not the cleanest one. What we wanted to test here is the method, the implicit method, not the boundary condition, which is another very big problem, which we have been thinking a lot. Well, you know, the boundary condition is always a complicated matter, but we have to deal with everything because everything is new. So say, okay, let's just solve the boundary condition issue in a simple way and test the method. So what I'm showing here is for the initial data 1, what happens when we vary K3. Remember that K3 is the coefficient multiplying the terms which have the 6th order derivatives. So remember that for people who do numerics, I need to consider difference operator up to 6th order and put all this information in the matrix that I have to invert. So it's a little more. I fixed K2 to 0.1 just for, I chose this scale. What I see here is the evolution of the field at different snapshots of the evolution of the field. If you can see, there is behind a black curve. This is the wave equation with K3 and K2 equal to 0, and the comparison with the case in which I turn on the anisotropic scale. And what we see is, I even put here the labels. Sorry for that. But when we increase the value of K3, we have a faster growing of the modes. So this here is with a small K3, and this here is with the biggest K3. So the growing is faster, and those modes enter first in the killing horizon. This is the killing horizon, not the universal horizon, because remember that in our new coordinate, the universal horizon is in -infinity. What else? Well, of course, what we can see here is an explicit. We see explicitly the dispersive nature of the solution, unlike the wave equation, which has just these two usual pulses. We have here a cascade of modes that travel at different speeds because there are different modes with different k. So if you compute the group velocity, we'll have different velocities. And another physical interesting thing is that when we increase K3, we start to see a bump growing close to the killing horizon. This is a bit weird because we know that the system is stable. We prove analytically and numerically the stability of the method with the von Neumann analysis and also the convergence. So all those tests are totally passed. I mean, they are correct, but still we see some bump generating there. I'm just finishing. And for the initial data 2, with the ingoing, approximately ingoing pulse, I'm just showing what happened on the other case. The other case, we fix K3 and we just move K2. And the behavior is practically the same. And also we can see that when we increase K2 here, fortunately I put the label, we can see that there is also this bump that could imply. We are still working on this with Mario, with my collaborator in Barcelona, and instability of the universal horizon, which is something that is not proven, even though in a theoretical way. So if we have at least a numerical proof of the instability of the universal horizon, this is not the universal horizon, but something similar we think that will happen in the universal horizon. So that would be interesting. We are working on this now. Just in order to finish, the effect of the centrifugal barrier, just as always, this the effective is a potential that has this form. You can see that for B larger and larger L's, this is more difficult, this modes to enter the horizon because of the effect of the potential barrier. You can just see this by looking the plot of the potential, and from the numerical point of view, we could also verify that this was actually true. You can see that, for example, the mode, this is the potential in logarithmic scale, and this is the snapshot of different times of different modes of our solution. And in particular, the modes when increasing L are sort of damped when entering the universal the Hilly horizon. And this makes explicit the role of the effective potential in the equation, which is something that is not surprising, but we at least need to verify. And the last slide, we did the usual conversion test, in which we assume that we have an exact solution, and we have either constructed analytically, then I can tell you how. You need to modify a bit the equation and add a source, or think that the exact solution is a very, very high resolution solution, and then you compare with lower resolution solution or similar. What you will see from the analytic point of view is that this difference, the exact minus the numerics, scales as delta x squared plus delta t squared, which is usually what happens for second order accurate schemes. But also, unfortunately, there appear terms which are products of delta x and delta t. This in general doesn't happen. For example, in the wave equation, it doesn't happen. So it was a bit difficult to test these second order conversions. So what we decided to do is just rescale delta x by lambda times delta x, and the same with delta t. So when we put this here, we get a lambda square here, lambda square here, lambda square here. So this difference should scale not as order delta x square or order delta t square, but order lambda square. So we did 3 simulations with lambda, I think, 1, 1/2, and 1/4, low, medium, and high resolution. Compute the usual quality factor, I think, conversion factor. It should go as 2 to the order of the method. We expect that the order of the method is second order because of the accuracy of the difference operator we were using. And well, you can see that for different values of K3, this method is approximately second order. Remember that we have also the issue of the boundary conditions, so a lot of things that could and should be improved if we want to tackle the problem of the collapse in Orava in a more serious way. But this is, as I told you at the beginning, the very first step towards a more ambitious project, if you want. So we are happy, at least we obtained this almost second order conversion. I think I said everything. We have the implicit scheme. We apply the implicit scheme for the Lifshitz field, which is the toy model of Orava. We found the centrifugal barrier and how to modify the dynamics of different modes with different L angular numbers. We want to obtain this method for nonlinear equations. The method is exactly the same. We just need to iterate the nonlinear part somehow. We tried with the nonlinear heat equation and it worked. So this is nice. At least we have to deal with this. And of course, the final goal is to apply this method for spherical collapse, at least in Orava gravity. If we are lucky and everything works, we would like, of course, it's my dream, like to try to simulate, for example, a binary in Orava and see what happens. And if there is some interest, today we were discussing with Alex, if he was also interested to apply some of the theories in his hyperboloidal that you probably know about very, very well. For some other hyperbolic problems, so I'm happy also to show the method, to share the code, to collaborate with that. And so I think I'm done. So thank you.
Perfect. Thank you very much. Yeah.
Sorry for all the technical questions that I'm not an expert on.
No, no
On
problem.
conformal diagrams, and I mean, I'm most numerical, but thank you.
We still have a few
Yeah,
minutes for questions. So
About the anisotropic scaling.
Yeah.
Two questions actually.
Yeah.
One is in the Lifshitz field theory. We have an action for that.
Yes.
Is that an exact scaling symmetry or only asymptotic in the sense that if you just play with the action and you do that scaling,
The
some terms
anisotropic scaling in the case of Forava is in the limit of high frequencies.
Okay.
So it's not,
Okay.
but in the Lifshitz case, it's exact.
Yeah.
Yes, because it's already, I mean, the Lifshitz field is already the high. No, wait.
so
No, they have, sorry, they have the
That's
same,
the second
I mean, they behave similarly,
Okay.
but always in the high frequency. Sorry.
And then related to that, this the previous slide, I think.
Yeah.
From,
The conversions?
yeah, the conversion.
Yeah.
Exactly. So why don't you have also anisotropic scaling in the lambda there? And I would expect that naively.
You mean in this?
Yeah, so you scale x, delta x with lambda, and you would scale delta t with lambda cubed, I think.
No, remember that this is not exact. You have also terms going as terms which are cubed.
Yes.
So probably if you want an exact scale, you will probably get something like this. But if you consider higher order terms, this is the leading order. And for testing conversion, we just need to see how things work at leading order in lambda. So I think there are different things, because what we need here is, remember that we are not saying here the scaling of the solution, but the scaling of the difference between the solution. It's not necessarily have to have the same. I think the same.
If the symmetry was exact, probably you would have to choose lambda.
That's why you asked me
Yeah.
if the symmetry was exact or not. Probably. Okay, but yes, I mean, for the difference, I was expecting something scaling as delta x square and delta t square, because our finite differences operators are second order arc. The reason why I'm adding this lambda scaling here is not because of the anisotropic properties of the theory, but just because we have this unlikely term going as delta x, and that probably there will be order. I mean, if you consider the order delta cube, you will have something like delta x squared, delta t, but those are not leading order, right? If lambda is small, those are terms which are subleading. So with this, at least was enough for numbers.
So, if we go back to the slide with the conformal diagram.
Yeah.
I was going to ask, so the profiles of these slides,
Mhm.
of the slices, because they look very much like trumpet slices.
Mhm.
But
I remember that you work on trumpet slices, but I
yeah,
don't
no,
have
if
the
they
details.
look, if you plot them on a diagram, okay, I'm talking about GR,
Yep.
blah, blah, blah.
Yep.
If you plot trumpet slices, they look exactly like that, towards like going up to the top left. But I mean, in this case, these slices, they are given by, I mean, are you like using this condition on the frame? That you
Yeah,
talked about
this is
before?
in the preferred frame. So this
Okay.
slide is probably that. Probably this is just a sketch of the Penrose diagram. But what I can assure you is that those are the preferred foliations, so they are normal to the E.
Okay, this is very
Yeah.
interesting because
And the ether is time.
right. No, because that's very interesting because I mean, if you calculate trumpet slices and structure, I mean, they look qualitatively the same.
Have something to say. Okay.
It's very interesting.
Well, I should review the conformal diagram of
Yeah, we can talk about that.
this foliation, but this is for sure, because in Orava you cannot do things outside the preferred frame, because by construction the theory is made up in that frame. And in your trumpet case, the normal is not always time-like, right? I mean, at some point you told me that they could
Okay.
become null or something, at least in the boundaries.
I mean, if you think about hyperboloid, definitely becomes null at
Okay.
right, like the other side.
Sorry,
But
hyperboloid.
within the trumpet, let's say the part which is like inside of the whole black hole horizon, like
Mhm.
okay, let's say the horizon.
Yeah,
Then
this is
that's
an
pretty much
event
the same.
horizon.
So I'd like to understand it better, but let's talk about it.
Sure. Yeah.
Do you have more questions?
I wanted to ask a question.
Yes.
Yes, go ahead.
So I think that it's in the next slide. So you have some numerical results. More, yeah. Here, this is good. So these results are very irregular. I'm wondering if this is the what you expect physically, or is it related to the numerics of it?
So irregular in which sense? Because both stability and conversions were proven for these schemes. So
I mean,
really we were there one thing that we were expecting, which is the cascade and the anisotropic behavior of the different modes going there. The mess that happens here and here were not expected, but these are the solutions we got for transition time until some long time, which we noticed this bump. So probably the plots are a bit confusing. What I wanted to show here is that sort of stability close to the horizon for different values of K3 until some point in which if you sufficiently increase K3 for kappa 3, you will start to see that there is a bump that starts to bother around.
so the fact that the plots are so let's say non-smooth in R star is what the actual solutions have.
They are
like
smooth. They are smooth in our stuff. They are ringing, probably.
yeah,
but
okay,
they are
that's what I
smooth.
mean.
There is a previous work by Niayesh Afshordi, I think Shinji Mukoyama, in which they solved something similar, but using an explicit scheme. Their objective is to see super radiance in that paper. It's a very nice paper, and they also see ringing. We didn't compare our solution with their solutions because for some other reason in the way they choose the parameters, they were more restricted because their method was actually explicit. But the profiles of our solution is similar to some of the solution they show, in which they also show ring.
Okay,
I could say that yes, they are a bit messy, but they are smooth and regular. At least in the physical region I am showing.
yeah, thank you, that's what I wanted to know.
Okay. Thank you.
David, last question. Sorry? Okay, well, let's thank
Okay.
Marcelo again.
Thank you.
If you enjoyed the video, like and subscribe.